So welcome to this course on forecasting. The topic today is the first of a series of lectures that will lead to Lab 4, where we will review what are the classical techniques for forecasting. Before that, let me recall that in the last 4 weeks of the course, the topic is your mini project, performance evaluation mini project. For now, what I'm expecting for you is to give a one-paragraph definition. This is due April 14. You can have all details on Moodle of what your project will be. And I would like to read this at the latest on April 14 and discuss with you to check if this is okay, in particular in terms of size. So the project is typically based on a project of your own, but it can be, if you don't have such a project, it can be based on paper or some available simulation resources that are available online. You can do it in a group of 1 or 2 students. In most years, the same groups as for the labs. And it typically addresses the performance of something that you've been involved in. If you don't have such a thing, we can find something for you, or we can give you hints on where to find something. You might also address a methodology issue rather than a case study, so everything is open. Please talk to us. The size of it should be the size of 2 homeworks. So it's 4 weeks of work for about the same duration per week as you are supposed to devote to homeworks. Right? So it's important that you think about it early in the process. So try to think about it as early as possible. The deadline is the ultimate deadline, but you can already post your one-paragraph definition if you have an idea already, and then we can have an interaction to talk about it. Well, now to forecasting. When we do a performance evaluation study, we have seen that we need to identify factors, and then we will have to identify also load or benchmark our load models. Right? So the nature of the load is usually something we can find by looking at the literature or based on experience that other people had before. The nature of the load is, for example, when we're testing a website, then we send typical requests. So that is something that is typically easy, not easy, but something that can be identified with in a fairly objective way. What is more difficult is the intensity of the load. Imagine you're working on a data center and you have to dimension it so that it will work for the amount of work it will receive. Right? For that, of course, if we can forecast, that would be wonderful. Forecasting is a magical exercise. Anybody can forecast things, but of course, the only law of physics that we're 100% sure about is that the arrow of time goes one way. So it's impossible to know exactly what the future is about. However, as engineers, we are able to say something about the future, not everything, but something. For example, if you're handling a data center and you observe that there is a growth at some rate over the past 6 months, then you can infer that in the future the growth will continue, and you should be prepared to such a growth by installing new servers, for example, here. Same if you have an infection that is happening somewhere, natural infection like we're unfortunately all experiencing now with COVID, or computer infection that is even closer to our area of concern. Then if you see that the growth is exponential, you can easily know that in 6 hours from now, for example, your complete system will be down. So take-home message is you should forecast what can be forecast here, and also be aware that what you forecast has some uncertainty. So not surprising for this course, we will see techniques for forecasting, but also for quantifying the uncertainty of your forecast here. And of course, we can be completely wrong. We can have a model of growth of our data center that we engineered in the 2 first months of the year 2020. And then in the 3rd year, everything changed because of lockdown. And then those changes were probably not in your model. So things that are not in our control, well, they're not in our control, we shouldn't worry about them, but we should worry about the things that we can forecast. In probabilistic terms, it's interesting to understand what forecasting is really about here. So the first thing is, assuming I have observed some series of data, YT, so YT is one data point or a complete set of data, indexed by time here. Typically, we keep time discrete to make things tractable. And the forecasting problem consists in having observed everything up to some time t, being able to say something about what will happen at time t plus L. L is called the lag, that's the number of steps in the future. A full forecast is the conditional distribution of the future given the past. Of course, when I say conditional distribution, that assumes that I have a probabilistic model of my system, and that is part of the forecasting story. If we don't have a probabilistic model, then it's hard to give a forecast. That's the full forecast. So a full forecast is not saying, I think that YT plus L will be this, but I'm giving the distribution of YT plus L, which in concrete terms, in mathematical terms, is a conditional distribution. A point forecast is one value, it's our best guess, and very often it is the expectation of this distribution, so which is written expectation of YT plus L given all the past Y1 to YT. It can be the mean, it can be the median, depending on whatever computational means you use. And the prediction interval is an interval AB that is computed at time t, depends on the value y1 to yt, and is such that the conditional probability that the future is between those two levels, assuming that here y is just a single number, is larger than some threshold, close to 1 here. Very often 95%, but this can vary depending on the field here. This is in the case where y is a number. If y is not a number but a vector, then we would have a prediction region with a similar understanding. The probability of being in this prediction region, conditional to what we have observed, must be larger than something. And the goal is to be able to compute point forecasts and prediction intervals. There is one method we have seen already that we can apply for free, which consists in using regression model. So this is very often used, in particular in contexts where we want, for example, to instrument a system. For example, if you have a computer memory or a data center, and you want to take actions based on what could happen some point in the future. Here's an example showing by this curve here. This is data from a US operator about the amount of traffic on the communication link. And this operator wants to resell some of the capacity at different prices also. So needs to know what is likely to occur in the coming hours or days here. A model can be fitted to this. Here is the model we fitted. In black, we have the traffic, and in red, we have the fitted model. We see that the fundamental, a first order property of such a traffic is that it is periodic. Here, the time scale is such that one period is 24 hours here. So of course, traffic on an internet link in a given country or continent is very different at night and during the day. And this is the first order behavior we have. So capturing this behavior is easy, for example, with a sine function. So this is what we could do. We fitted to the past data periodic sine function, which has here 3 parameters, a, b, c, which are the constant term, the coefficient of the cosine and the coefficient of the sine. And if we put it in this way, this is a linear regression model, because the dependency on the 3 parameters to be fitted is linear. Here, the period is given because we know out of band the periodicity corresponds to the daily activity, so it gives 24 hours. So we fitted this model, we obtained those parameters, and here we think, right or wrong, we think that the noise term is IID Gaussian, and we identified the standard deviation. So that is the thing we've seen in the past weeks. we can easily fit this because fitting linear model is very simple. We can use this to do a prediction. If we believe that this model will continue to be correct, and if there is no major disruption like emergence of COVID, probably it is true. So it's a good assumption to assume that at least in the short term, in the coming days, this model will be correct. So we have this model. And if we believe in this model, then the problem of forecasting is to say something about y at time t plus L. So I project myself in the future and I say this model will also be true in the future. Therefore, I have this property here for what will happen at time t plus L. In this equation, I have epsilon t plus L, which is the noise term. And in this model, the noise terms are all independent of each other. In particular, the noise term epsilon t plus L is independent of all the epsilons at time 1 plus 1 to t. In fact, it's independent of all the other epsilons. That's what IID means here. Since y is simply a constant, a non-random part, it's not constant as a function of t, but it's a non-random part plus epsilon. So knowing y is equivalent to knowing epsilon, knowing in the sense of knowing the random part in y. Assume y is given by a simulator. If I give you the simulator parameters, which is all those numbers, and if I give you the y, you know the epsilon, and vice versa. So epsilon is independent of these epsilons, therefore it's also independent of these y, because these y's are a function of these epsilons. Why do I say that? Well, because I need to compute conditional distributions. The conditional distribution of yt plus L, which is this quantity, is given by the conditional distribution of all that stuff, but that stuff has non-random terms, so they don't play a role. So the only thing that we care about is the conditional distribution of epsilon t plus L given the past, which is given the past, as we have said, giving the past in y or epsilon terms is the same. There is a one-to-one mapping from epsilon to y to y here. For example, if we want the point prediction, we're simply computing the expectation. So the expectation of yt plus L given y 1 to t is the expectation of this term, the conditional expectation, which contains all the constant terms, the non-random terms, plus the conditional expectation of this. Now, the conditional expectation is equal to the expectation because it's independent. That's what we've seen in the first week. Independence means that if we condition upon the thing, it's the same thing as not conditioning. So this expectation, because it's a noise term, is 0 here. So I can say that this conditional expectation is simply the constant term where I remove the noise term. So that is my point prediction. That's the best I can say, or at least one. If I want to summarize the future with one value, that's one value I can say, which is very often the only value that is given. So for example, on this curve here I'm showing the past data, and here I'm showing the prediction. So the last part here is the same as this, but the y-axis scale has changed. Here I have inflated the y-axis to show more. So the red thing here is the prediction. That's the point prediction. The blue is the truth that was not known at the time of prediction. We see it's not exact, but it's not so different. But what we would like is also a prediction interval with the band given by the dotted lines around the plane line here. How do we obtain it? Well, let's go back to what we wrote before. This is what my model says the future should be. Now, this big thing here, we said that's the prediction. So I can rewrite this by saying the true value at time t plus L is my prediction plus epsilon of t plus L. And my prediction in this case here is non-random. It's given by this term that does not have any random part. In general, the prediction might be random, but it's not random given that we have observed everything up to time t. That's by nature. The prediction I'm making at time t depends on everything I have observed. Given that I have observed those things, they are not random. The conditional distribution of this is saying this is a constant thing. So this is another way of writing this formula here. And now I want to find the conditional distribution of yt plus L, which is the same as the conditional distribution of epsilon t plus L, shifted by this quantity, which is a non-random part. Now, what can we say about epsilon? Well, we know that the conditional distribution of epsilon is the same as its non-conditional distribution, as we said a minute ago, because epsilon is independent of y. Therefore, if I want a 95% coverage interval for the conditional distribution, I simply take the 196 plus or minus 196 sigma. So with this probability, with 95% probability, epsilon t plus L will be in this interval, regardless of the values that we have observed for y. Therefore, for yt plus L, we shift all this by this quantity with probability 95%. Given that we have observed all the past, the future will be in this interval, which gives me this band of width proportional to sigma, that is my forecast for the future. It's a 95% probability forecast. That means out of 20 data points, there is in average, we expect one to be out. And if we see here I'm forecasting 25 points ahead of time. And I have one or two that are just at the boundary of the interval. So we see that this is a good coverage. It's a good prediction interval. So with this very simple model, we're done. We're able to say that the resources I need should cover this interval, at least with 95% probability. And this is how an operator today runs its network. It knows, for example, that at this period in time here, the load will be somewhere in this band. Therefore, I can, for example, plan to shut down some electrical resources to save energy, or I can resell some of the capacity here because I will not need it, and I have at least an uncertainty band about what I can resell. We can do that for the other example we saw last week about the virus growth data. We saw that the reasonable model is to fit the Laplace noise in log scale, and we had fitted it with this value here. Therefore, we can do the same exercise. What is a point forecast at time t? Well, the noise is zero mean, and is independent of the past. Therefore, the point forecast for the noise is zero. Therefore, the point forecast at time t plus L is simply the part that is non-random, which is log A plus alpha t plus L. And by the same argument as we've seen from the previous slide, epsilon t will be with probability 95% in the quantiles given by the Laplace lambda distribution. So eta is eta is the 97.5%. So plus or minus eta means with probability 95%, we are between those two values, which is given by a closed form from the exponential function. And that will give us a prediction interval for the log. So the log will be between, is in this range here, expressed here. And if we want a 95 prediction interval, we take the exponential, because the exponential function is an increasing function. So if log is between those two bounds, the true value is between the exponential of the two bounds, which gives me this here. So a 95% prediction interval here too is given in closed form, which is what I did here. We see that in log scale, the prediction, well, is not very fancy here. It consists in continuing the straight line and putting a band here of constant width, which is more fancy if we observe it in natural scale. That gives us this prediction here. We see that in natural scale, the uncertainty is fairly large, but this is what the model tells us, because we have discussed the different models, fitting in log versus natural scale, fitting Gaussian noise versus Laplace noise, and we saw that Laplace noise seemed to be a better fit. So this is probably the best forecast we can make about the virus expansion here. Voila, a little quiz. For this model, which is not the virus growth, but the periodic traffic on an internet link from an American operator, what can we say about the width of the prediction interval? So time 224 is the time t. That's the time at which we do the forecasts. I close the poll in a few seconds. Majority says B, which is true, but C is true as well. Admittedly, this is a bit contorted, but it's interesting to see why. Well, first we saw that the 95% prediction interval is plus or minus 196 sigma, so the width of the interval is twice 196 sigma, so A is true, right? The model is fitted with least squares. Therefore, we have seen that if we fit with least squares, we can estimate sigma square as the mean squares of residuals. So sigma is the root mean square of residuals. That's the formula we have seen for least square. Here it's even linear, but least square in general says that the score function is the L2 norm of the errors, but also it says that the estimate of sigma is 1 over the number of data points times the L2 error. And so for the variance, the estimated of sigma squared. So sigma is the root mean square of this. So this is also true. Now the last point is also true because the residuals are also equal to the forecast error, right? Because if we look at the value at time t, which we could have seen, which we could have forecasted in the past. So assume at time t minus L, I forecast the value at time t. The formula we'll have is this one. That's applying what we saw a minute ago. A minute ago, we were at time t and we wanted to forecast at time t plus L. Now we're at time t minus L and want to forecast what happens at time t. So the notation here, y hat of t minus L means it's a forecast done at time t minus L with L steps ahead. So that's the forecast of yt. And we see that yt is equal to its forecast plus epsilon. So another, for least square regression models, we have another interpretation of the epsilon, which is the error of the model. But if we think of it in terms of forecast, it is also the forecast error. So both are true in this specific case. Now, what we will see is for other models, how we can interpret the forecast error. Now, if you followed this course carefully, you probably are a bit worried by the fact that I was a bit sloppy about the one part of it, which is I assumed that the model that I have is a perfect model, but in reality, it was estimated. I estimated the model parameter theta from the past data, and we know that when we do that, it is not perfect. We don't gain a perfect knowledge of theta, and this is why we do confidence intervals about theta here. So if we look at what happens on a very simple example, so assume we observe x1, xn, and we want to forecast xn plus 1, and assume that we have the simplest of all models that we already discussed yesterday, which is xn is simply equal to a constant plus noise. Not a very exciting forecast exercise, of course, but that is just to show how things work here. By doing that, we obtain an estimate mu hat of mu, and also, if we want, sigma hat of sigma. Now assume we want to do a point prediction for xn plus 1. Well, if we do use the argument I used a minute ago, we believe in the model. So we say xn plus 1 will be equal to mu plus epsilon n plus 1. Since epsilon n plus 1 has 0 mean, a point prediction of epsilon n plus 1 is 0. So my point prediction for xn plus 1 is mu. And since I don't know mu, I replace mu by mu hat here. And if I want a coverage at 95%, I will add a coverage interval, which is 196. Point prediction, sorry, we will, the point prediction for mu, for xn plus 1 is mu. Okay. Now I'm staying with my point prediction. My point prediction, if I want to be very accurate, is a bit uncertain because I don't know mu exactly, but I know that with probability 95%, the true mu is within this confidence bound. This is the confidence interval I obtained from mu. So this is the uncertainty about the point prediction. Now, if I want a 95% prediction interval, so I want a coverage interval, where I want to say with probability 95%, I believe that my next sample will be. That's different from the previous. Here I say with probability 95%, I believe that the unknown mean of my system is mu. Therefore, the best point prediction I could say is this plus some uncertainty. But here, that's not a very exciting thing in terms of prediction. In terms of prediction, I want to say where I will be with 95% probability for xn plus 1, not for mu. So I can do the same method as I used a minute ago for the previous cases. If I ignore the estimation uncertainty, I will say that the prediction interval is mu plus or minus 196 sigma. And if I don't know the true mu and sigma, I replace them by the estimate. When I'm doing that, I'm doing something approximate. And since mu is itself known with this uncertainty bound, and same thing for sigma, the question that arises is, what is the true uncertain interval? Well, this is given by a theorem that is in the previous chapter on confidence interval. In fact, we know that if I have exactly this case here, I have a sequence, I want to predict the last term and assume the sequence is ID and the noise term is Gaussian, means that's a Gaussian sequence. Then the distribution of the next point minus the estimate that I have is given by this. It's a student distribution, which means we have seen the student distribution. We know when n is large, it's close to a Gaussian distribution. But the prediction interval that we obtain is the eta. Eta prime is close to the 196 that we're used to. But here, there's a square root term of 1 plus 1 over n. So in some sense, we add the two terms that we saw before. 1 over square root n is the uncertainty we have in the confidence interval for the mean, and 1 is the factor we have for the prediction. And exactly, if we want to do things, we put everything under the square root and we add them, and that's a true prediction interval. So if we do it numerically for n equal 100, an exact interval that accounts for both the uncertainty of the estimation of mu and the uncertainty of the future is this, mu hat plus or minus 199, whereas the approximate would be 196 here. So what it seems here is that the estimation uncertainty is much smaller to the prediction uncertainty, therefore ignoring it is probably okay. We see that the estimation error decays in 1 over square root of n and is small for large n, whereas the prediction uncertainty does not decay with the number of points we have used for estimating. So in general, there are exact formulas. If we do linear regression, instead of this very simple model that I showed a minute ago, the formulas are one notch more complicated. Those are formulas similar to what we saw yesterday. I will not go through them in detail. The take-home message is simply that there exists closed form formulas that use the student distribution. When we have a linear regression model, that means we assume there is linear dependency on the parameter, and we assume also that the noise terms are Gaussian IID. So if we can believe in those assumptions, we can compute everything, including an exact prediction interval. So I did this for my example here. On the left, I'm showing the dot dashed lines are the uncertainty bounds here in green and red when we apply this formula. So we see that the coverage at the prediction interval is in fact not affected by the prediction, the estimation uncertainty, when I've used 220 points for doing the estimation in the past. In contrast, if I use only 24 points for doing the estimation, I see that the green dotted lines is slightly above the red dotted line. So the red dotted line is the prediction interval I have if I ignore estimation uncertainty. The green one is if I incorporate it. I see that there is a small difference here, but again here the number of data points I've used to estimate the model is very, very small. It's the same order as the number of points used for prediction, which is a very atypical case. The green band in the middle is the uncertainty on the point prediction. So there is an apparent paradox here, which is that the uncertainty on the point prediction is not completely negligible, but when we combine it with the prediction uncertainty, then we can ignore it. So take-home message, when we use a fitted model, there's some uncertainty that adds to the prediction interval. In most cases that are reasonable, that is when the fitted model is fitted on a reasonable number of data points, the model uncertainty is the major source of the prediction uncertainty, and therefore that justifies the common practice when we do predictions that consists in ignoring the estimation uncertainty in the prediction. If you are fortunate enough to do linear regression with Gaussian errors, then there are exact formulas, so the problem does not arise, but that's a fairly rare case. Voilà, that's our first pass on prediction using regression models. We will see other methods, but before going there, we need to discuss a problem that is well known in other contexts, in any course on learning, machine learning in particular, which is the overfitting problem. So if you had a course on machine learning, you probably know all that stuff. If you do, then that will be a revision. If you don't know, that's the opportunity to learn. Here I'm showing several predictions for the same model here. Here I had fitted my data traffic on an internet link with a cosine function, combination of cosine and sine, which means a cosine function with a phase shift. So here I had improved the model by adding a polynomial term, because in fact, if we look at the data over a long period, which is what is in fact done for this model here, we see it's not very visible, but we see that there is a growth. If we take the average, for example, over 24 hours, we see that there's a small non-linear growth, a small convex growth. So it's probably a quadratic growth. So one idea is to add a polynomial term to the model, which is nice because that keeps the flavor of being linear regression. The unknown parameters are the coefficients of the polynomial. Similarly, we see also that this is not really a sine function, right? The shape is not a beautiful sine function. There is a slightly divergence from this. So one way to model this, as you know from Fourier analysis, is to add harmonic terms. So we add to the periodic part more harmonics. Here, H harmonics, and D is the degree of the polynomial. So this is my basic model we saw a few minutes ago. This is the similar model where I fitted a polynomial of degree 10, so 11 numbers to fit, and 3 harmonics. We see that we have a better fit because we're able to have a periodic curve that fits the average irregularity better here. And now I do a prediction with that. The prediction with the predict is in red, the prediction interval is the green band, and the true values are the blue terms here. As you see, this prediction for the second model is completely off. In fact, the predicted polynomial forced us to go down dramatically here, because it was the only way a polynomial of degree 10 could fit this function here, which is completely wrong. That's an instance of overfitting where more is not better than less here. Here I had too many parameters to fit my model, and by fitting too many parameters, I was in fact removing entirely the noise. I had a model that is pretending there is no noise. If I have enough parameters, I can fit any function exactly. If I fit any function exactly, in learning theory, we don't learn anything. So in order to learn, we must allow that the noise remains noise here. So having the better fit in the past does not give the best predictor here. In the extreme case, a model can fit exactly the data, and then it's not a model of the data, it's just a repetition of the data. So how can we avoid overfitting? Well, the first important thing is to be aware of this problem. Too many data points, too many parameters is not a good idea. Rule of thumb is that the number of parameters you have in your model should be much less than square root of the number of data points here. But how to know exactly how to do? Well, the data science methodology is to reserve some data for testing. So we can fit the model by not fitting it over the entire interval, but we keep, for example, 10 data points that we know they're not needed for the prediction, but we fit the model before those 10 data points, and we test the prediction ability by plotting here the prediction error. Then we will fit the model that has the smallest prediction error. So here, for example, I chose 3 harmonics, and I looked at what is the best polynomial degree. In terms of estimation errors, they're all quasi the same. It's not very easy to see, but we see that the estimation error slightly decreases, but we see that the best prediction here is with degree 4. When we go above, then the prediction error increases here. So this is what this methodology would give us, which is a method that is very often used, makes a lot of sense. However, there are other methods that are a bit more radical that are based on information criterion. So an information criterion is trying to find what is the best way to model the data without having to use test data, without burning some of the data. So we use all the data, and by another reasoning, we try to see what is the optimal number of parameters here. And the idea is to add a penalty term to the score function. Remember that the score function is what we use for fitting. And we've seen 2 typical score functions when we have L2 or L1 scores. And where did we lead? How did we come to these conclusions? It is by looking at the likelihood, or very often for tractability, we look at the log of the likelihood of the data. So we maximize the log of the likelihood of the data, which means another way to put it is we take minus the log of the likelihood as the score, because the score wants to be minimized here. For least square models, in fact, we saw that this is exactly equal to n log of the estimated residual noise square, the mean square noise here, so sigma hat, plus a constant that disappears in the optimization problem. So instead, if I say I have a model that can have a large number of parameters, of course, I will find the sigma hat that is as small as possible. But to avoid the overfitting, the idea is to add a penalty term. So Akaike's information criterion is one of these systems that adds a penalty term. It takes the likelihood, or minus factor 2 for some reason, and it adds a penalty term, which is the number of parameters that we have chosen here. So for example, if the number of parameters is the number of dimensions of the vector beta when we have a linear regression model here. So for a linear regression model, the IKK information criterion is given by this formula. It depends on the estimated variance, which is the mean square error of the model, times 2n log of this, plus 2p, where p is the number of parameters of the vector beta here, plus a constant, which will be the noise, etc. Since we minimize the criterion here, we don't care about the constant. So this is one trick. Now it appears as a pure trick, but there is an information theoretic interpretation of this, which is given here. IKK information can be interpreted as the average amount of information which is required to describe a new hypothetical sample of the same data when we estimate the model from one sample. So this is an excursion into information theory. One way to interpret information is to say how much bits I need to describe an output of a given system. So here I've observed the data y. Then I estimate y using, for example, least square and p degrees of freedom for my parameter beta here. Once I have estimated the model, I can compress a next output of the same model because I know the distribution. So here I'm doing two things. First, I'm assuming I know I have an explanatory model for the machinery that produces y. In the terminology that we've seen so far, it means a simulator. Right? Estimating the model means writing a simulator. We fit the models like we did in the polynomial and sine functions. We can view that as the parameters of the simulator that we think has produced the past data. Now, if we know the simulator and we do a thought experiment, let's say, let's do a replay experiment where the simulator will produce, the true simulator will produce a new output, and I want to compress it, describe it with as few bits as possible. If I know exactly the simulator, I can predict what it will do, and in order to describe the output, I only need to give the error, how much deviation there is from the average case. So if I have a good model, the error will be small and I need fewer bits to describe it. If I have a model that's completely off, then everything is error and I need to describe everything. So this is capturing the fact that knowing the model well can be measured in the amount of information that is required to describe a new sample. And this approximately is exactly, if the model is true, is exactly given by the IKK information criteria. So if we want to optimize a system, we should minimize the IKK information criteria, because that means in order to do a prediction in the future, we have the most condensed and the most powerful information if the information criteria is as small as possible. Other information criteria are used in practice, although the IKK one is the most standard one, but very often some papers that are very much rooted into least square use different penalty terms. Bayesian information criterion is defined for linear regressions model with a slightly different weight here, penalty term, than IKK information criteria. It weighs it with log n, where n is the size of the sample. Here, as far as I know, there's no real theoretical, well-grounded justification, but empirically, it works well. So let's try those tricks on our data. Here, I remember this is the fitting. I did it for, I showed them different value for one polynomial of degree 1, so linear growth, and I test a number of harmonics. I see that the prediction error remains fairly constant and high. But if I look at the IKK information criterion, which is the blue curve here, we see that there is a minimum at 2, then it starts to increase, which is also slightly visible here. And if I use the BIC, the other criterion here, it's very similar here. So the best model here is for h equal 2. In this case, we see that all criterions agree, which is good news. If I use here a polynomial of degree up to 10 with 3 harmonics, then things are not as nice. We see that the IKK information criterion says that the best model is at 10 here, which is not correct here. We've seen that the prediction of that is very bad here. So this is the limit of this theory. Take-home message is I-formation criteria are not able to identify the best model in absolute terms because the polynomial models are not at all a good class of models here. However, if within a certain class of models that are well known, we have, based on past experience, we have the impression that a certain class of model would fit, then the IK information criterion or the BIC will be able to expedite your fitting, because they will tell you exactly how many parameters you should use. Voila, that's all we will see for today. We will continue next Tuesday discussing how to put all of this into practice, and also using an important ingredient for many time series data, which is linear filtering. Enjoy the work and the week, and as usual, I will stay online, and we can talk via the chat or any other means. Bon travail!